Yeah, like maybe we'll end up looking for more problems. Okay, so let me make the problem another line. That looks a little better. Thanks for joining, Animal. So this is 2016. So I would hope this is a little bit harder. So we have a triangle ABC with in center I. All right. So I is the center of C and K. So we have this kind of Sharky Devil configuration, right? So we have the foot of the perpendicular from D to EF. This comes up a lot. And it's usually worth drawing a couple other things when we do this, but I'm just going to draw what the problem says for now. So the circumcircle of AIB meets the incircle at C1 and C2. And the circumcircle of AIC meets it at B1 and B2. Interesting. So it's whenever you see those, it's almost always probably worth drawing the circumcircle of ABC, right? Because those, we could use the in-center, X-center lemma then. And I bet it's probably also worth drawing this circle because this point is collinear with KI and the antipode of A by Sharky Devil theory. So G, K, and I lie on a line and they pass through the antipode of A. So let's draw those other points. B, so these should be B1 and B2. And then these points are C1 and C2. And we want to show that the radical axis of, oh wait, what did I just do? Oh, I switched them. It should be the other way. This should be, this is confusing. So this is B1 and this is C1. And this is B2. And the other one is C2. That's weird. Let me hide this. So let me just draw DK. And let me draw the line GK. Let me draw this line, which passes. One sec. So that's going to pass through the antipode of A. I don't know how much that would help, but I'm just going to draw it for now. And then we want to draw the circles we're actually talking about. So B, B1, and B2. I mean, maybe it's just easier to show, so the midpoint of BK. So we're going to call that M. Let's check the chat. Oh, it's all right. So we want to show M has the same power with respect to those two circles. B, B1, B2, and C, C1, C2. Oops. B, B1, B2, and C, C1, C2. So a lot of stuff in this diagram. It almost looks like these concur. I doubt they do. Yeah, they don't concur. So yeah, it's a pretty picture. So maybe I should erase these two. I mean, I feel like they could be valuable though. Like this, no, we don't want to erase them. Let me draw BI and CI. Maybe they pass through something. Yeah, like it looks like BI. It looks like BI. Well, I'm not sure about that actually. Yeah, no, it doesn't pass through that point.
I think I found something which I didn't prove, but like this. Add a midpoint of EF.
The midpoint of EF. All right.
Yes.
All right.
Then that point should also lie on the radical axis, and it is really good because actually Gergone point will lie also on that line.
A what point?
Gergone point.
How do you spell
intersection, that? Intersection of BE and CF.
Oh, the Jirgan point. Okay, yeah, sorry.
So it is pronounced Jirgan.
Jirgan. Yeah.
Okay.
Or yeah, I don't really know, but yeah, you're probably right. I probably just didn't know. So how do you know? How did you know that the Jirgan point would lie on the radical axis if the problem's true?
Well, I don't know that it lies on the radical axis, but I do know that the Gergone point lies on line MJ.
It lies on line MJ. Ah, that's like a famous theorem, I guess.
Yes, because Gergone point is the symmedium point of triangle DEF, and that is like a theorem.
Okay. Yeah, the symmedium point. So that's I think it's the Schwatt line, right? Like you have MJ and that's the median point are collinear. Yeah. Interesting.
So maybe we can show that Gergone point has the same power, or that midpoint. That may be easier.
So how did you know that J lies on the radical axis of those circles?
I don't know, but like just
it looks
tried
true.
and it looked like that.
Interesting. All right. So it looks like, whoops, sorry. So that's an interesting observation. So it looks like all these points lie on a line.
Can you hide the circumcircles of AIB and AIC?
Yes, although that's kind of how we define B1, B2, C1, and C2, right?
Yeah, but we can simply label the x-center, the midpoint of x-center and I.
Okay. So hide this, and the midpoint of arc AB, you mean?
Yes.
Okay.
It's going to be their centers.
Yeah. All right. Let me this point and that point. So basically O is the circumcenter of B, C1, I, C2, and A, right? And same with P, right? is M, sorry, I never answered your question on if M is the midpoint of their common chord. Let me check. It looks, no, M is not the midpoint of their common chord. Is B1, B2, C1, C2, and J seem collinear. Ah, interesting. So really we want to show that B1, J, and B2 are collinear.
That would actually prove that the J is on the radical axis.
Oh yeah, yeah, no, that's kind of just equivalent, yeah. Yeah, because that would mean it has the same power with respect to both circles, because yeah, okay. So how do we show that? Does KD, no, KD doesn't pass through the midpoint, but I think GD passes through them. So AI and GD, I think, concur on the circle. I don't know if that helps. So like we have AJ and I and GD meet on the circle. Whoops, didn't mean to do that. Point Q, L, N, E, and F are cyclic. Interesting. I'm going to go draw that in just a second. L, N, E, and F. Oh, whoops, that's not N, sorry. L, N. So I'm guessing that's probably power of a point. Interesting. Okay, so yeah, maybe it's worth drawing the Gergonne point too. I don't know if yeah, there's too much stuff. Yeah, I'm just gonna leave out the Gergonne point for now. But if you guys see how to use it, yeah, just let me know.
BB1 is equal to BB2.
BB1 and BB2.
Yes.
Interesting. Okay.
Because of the radical axis, I guess.
Wait, sorry. I want to use this. BP CC1 is equal to CC2 then. Wait. Oh, no, because I made that N instead of C2. Okay. Yeah, because the circumcircle of AIB, the center of it is O. So yeah, by symmetry, since C, I, and O are collinear. Yeah, so yeah, I see what you're saying. So basically, C1 and C2 are reflections about the angle bisectors. C1 and C2 are symmetric about CI, and B1 and B2 are symmetric about BI. So maybe that helps. Yeah, so there's a lot of symmetry here. We have to show that M has the same power with respect to those two circles. Or the Jergon point. I, AIC, and AIB. So that, okay. So maybe, yeah, I'm trying to figure it out. Hold on a sec. So we would have C1, C2, B1, B2, and yeah, what's the radical axis of AIB and AIC? It's just AI. So yeah, I think B1, B2, and C1, C2 concur on AI. It's a good point. Let's see. And oh, it looks like they concur on AI. We want to show they actually concur at point J. Okay, so we know that, yeah, B1, B2, and C1, C2 concur at some point on AI, and we need to prove that that point is point J. It seems like Pascal. Yeah, B1, B2, C1, C2, EF. Can we like use Pascal on that or something? It does seem like Pascal. Did we? Okay, yeah, we probably don't. So I drew all this extra stuff like point G, point H, point Q. We probably don't even really need them, right? Maybe it's just making things more complicated. I'm going to erase it for now. Maybe I'll just draw G, K, and I, but yeah, I don't need all the rest. I don't even know if I should draw point G, but one sec, guys, I'll be right back. All right, thanks for waiting. Sorry about that. All right, let's see. We have B, B1, B2, C, C1, C2. They're symmetric about BI and CI. And we want to show that M has the same power with respect to those two circles.
We proved that J lies on B1, B2, and C1, C2 respectively. Look at the chat.
Sorry, I didn't scroll up in the chat. I just look at the last comment. So J lies on both of those. Radical axis. But doesn't the radical, the circle with diameter AI, and so EF, EF AI, and B1 B2. Okay, so they do concur. EF B1 B2 and so AI and I is EF. EF, AI, and B1, B2 concur. Okay. So that does prove that. And so,
sorry, I can prove that. I can prove that B2, B1, B2, C1, C2 pass through the midpoint of EF.
oh, we just proved that, didn't? Or like with the radical axis theorem, that like B1, B2 passes through J and C1, C2 passes through J. But were you? I'm sorry. Go on.
No, I think that we haven't proved. We can use radical axis. Can you so more clearly? Sorry, I haven't watched. Can you say again?
So yeah. So I'm gonna write it. So Hakan wrote it in the chat, but I'm gonna write it out at right here. So this is the circle with diameter AI. This is the end circle, and this is the circumcircle of AIB. So those are the three circles that I think would prove that, and that Hakan just mentioned. So if you look at the circle with diameter AI and the end circle, EF is the radical axis. If you look at I, the end circle and the circumcircle of AIB, C1, C2 would be the radical axis of those. And if you look at the end circle, and if you look at the AI and AIB, AI would be the radical axis of that. So basically AI, EF, and C1, C2 are concurrent. Or inversion. Makes sense? And then once we know that, so I think we know that J lies on Ln, right? I think we could prove that. We just need to show that M also lies on it. So yeah, if we show that
We
Jergon,
proved that J lies on MN.
we proved that it lies on J
LN.
lies on Ln. Yeah. So we basically, I mean, we could let this line intersect DK at M prime, let's say, and then we want to show that M prime is the midpoint of DK.
Maybe projecting some points because dk is parallel to AI, and we have to prove the midpoint.
So yeah, maybe we could project through J. Let's see. So basically, if we extend AI to meet the in circle, let's say we did that. Then I think we want to show, I don't know if this, how much this helps. Okay, but basically I'm projecting K M prime D infinity through J onto the in circle. So we want to show that N D H E is harmonic.
J is not on the in circle, so you can't project there.
But it's weird. There's some problems I've done where, yeah, J's not on the in circle. Can't do that. But I don't think the problem is that, because I think you can project through a point that's not on the circle. I think the problem is that these 3 points aren't on the circle themselves. But yeah, I don't know. Okay, so let me get rid of that point H that I just drew.
Can you label the midpoints of DF and DE?
Yeah. Ah, interesting. Looks like they lie. I don't know if that's obvious, but it looks like they lie on B1, B2, and C1, C2.
Yeah, actually, it's obvious because B1, B2 is parallel to DF, and J is the midpoint.
Okay. Yeah. And then, so is this like Pascal? This looks kind of like Pascal's theorem, but not quite, because J isn't on the circle.
And then we could try to prove that HM, LN, and DK concur.
HM, LN, and DK. Kind of like that. Yeah, it looks so close to Pascal's theorem, but it's not. If only J were on the circle. Have we used, yeah, we want to use that DK is perpendicular to EF somewhere. Maybe L, yeah, because M is not the midpoint of LN. I think Hakan asked that earlier, right? Yeah. Let me, instead of M, let me rename this something else. J. I don't know. Whoops. Yeah, we have to use, let me try projecting again. Like, what if we project through F? So if K goes to E, so E and D are fixed. I don't know if that's that good. Does HC intersect BJ? Also lie on LN. Let's see. It's HC. And yeah, looks like it. Since BJHC is cyclic, maybe we can go from there. So it almost looks like M prime lies on the circle. Yeah, it's hard to make M prime far away from the circle, but it's actually really hard. So I'll just leave the diagram the way it was. Oh yeah, that's right, they're collinear. So where we want, if we show they're collinear, that would solve it. So like maybe we could label this point and then but yeah, we have to use that DK is perpendicular to EF. So maybe I could use that like, I don't know if I want to use that like K is the intersection of GI and EF, or how I want to use point K. All right, let's spend like 10 more minutes on this and then we can move on to the next problem. But I like that idea that BHJC is cyclic. Let me draw the center of that circle. I'm just curious here. maybe we could draw this point and show it's collinear with the Jergon point and J. Oh, I shouldn't have called this J actually, because that was J. Let me call it I don't know, Q. Then this is J. Let's see. Should I draw the Jergon point? I'm just going to do it. Don't. Yeah, I wish I could use that fact. I'm not sure how. This almost looks like Pappus's theorem. So we have this and this. Well, yeah, I'll label the center of it. So it's point M, I'll just call it R. And then maybe R, I don't know if R lies on AI. MD also passes through the intersection. Okay, so.
Okay, Michael. Okay, so first I could prove that J is lie on the radical axis.
J?
Yeah.
Oh, we've proven that J lies on LN.
Okay, so second, if you call CH cut BQ at one point.
Okay, hold on just a second. So CH and BQ.
Yeah.
Okay, so I'm gonna hide hide that just for now. Sorry. Whoops. Let me zoom in a little bit.
Yeah, just zoom in.
Okay, so CH intersect BQ. Let me call it S. Sorry.
Okay, so that point will lie on the radical axis as well.
Oh, really?
Yeah, because if you call CH, cut the circle C1, C2. Yeah, at a point.
Let me draw it. Hold on a sec.
Could you delete the line B in CF?
B, E, and CF. Yeah. No, you're right. That would make it easier. So.
Yeah.
Yeah.
and BS cut the circle B1C, B1, B2 at another point.
Okay. Did I do the right? So CH, yeah, that's right.
Yeah, and BH, BH too. BQ.
BQ.
Yeah.
All right. So this point right here, I'll call it U.
Yeah. So we will have a BTUC exactly.
BTUC by power of a point because TS times SU.
No. No. Okay, so I will prove BTUC exactly. So that ST times SC will equal to SU times SB. So S will lie on the right axis.
Okay.
Right? Okay.
Yeah.
So you have that BHI is linear, right?
Yeah.
Yeah.
Oh, I didn't even draw that, but that's a good point. Yeah, BH and I are collinear, and
Yeah. So
C.
Yeah, and so C, Q, and I. Yeah. So HB times HI is equal to F times HD, right?
Yeah.
And that will equal to HC1 times HC2.
Okay.
So and HC1 times HC2 is equal to HT times HC.
HC times HT.
Yeah. So
Okay.
BTIC is lie on the circle. So T will lie on the circle, the circumcircle of BIC.
Okay.
And U, and so the symmetric U will lie on that circle as well.
All right. Wow. This is pretty cool. So
yeah. So H is lie on the radical axis. S is lie on the radical axis. So now you just have to prove that J, M, and S is collinear.
Okay.
So you can delete all and just let we will just need a proof to prove S, J, and M is collinear.
Okay. So I can hide. Let's see. So S was we defined that as the intersection of B, Q, and CH, right? Or Q. Okay. So yeah, we can hide a lot of stuff now. So yeah, so S is the intersection of B, Q, and CH, and then we have J, and we just need to show S, J, and M are collinear. I see what you're saying. I'm just gonna hide a whole bunch of stuff. No, I don't want to hide the big circle, but actually I probably could, right? I don't need that big circle. I can hide like a ton of stuff then. Wow. Okay. I don't need that. I don't need L. Let's see how this looks. I can hide even more. Okay. Hide this. Hide this. Still, yeah, I think I need to click that to hide it. Okay. So we want to show that J, M, and S are collinear.
Maybe we can now show that Gergona point is on that line, like S, Gergona point, and J are collinear. maybe.
Okay. Yeah, I like that. So hold on. Call it U. So can we show S, U, and J are collinear? Then we don't even need DK.
Oh, really? U is like on that the request is as well.
To show S, U, and J are collinear.
Oh no. Oh, so that point also lie on the right axis.
Yeah, yeah, if we could show S, U is the Jirgon point. So if we could show S, U, and J are collinear, then we would have S, M prime and S, M, and J are also collinear. That would solve the problem. It almost looks like Pappus's theorem a little bit, but it's not. But yeah, this looks like a nice problem. So yeah, show that S, U, and J are collinear. That would solve it.
No. Could you prove that U lie on the right axis first?
That U lies on it. I could try to do that. So you want me to draw in those circles again?
No. Did you prove that?
No, we didn't prove yet that U lies on it.
Oh,
But we
okay.
proved
So
that.
because if U lie on the right axis, so U is the lemon point, the concur of three symmetrian.
Mhm.
So by a theorem, J, U, and midpoint of KD is collinear.
Exactly. That's what Hakan was trying to, or was it? Sorry, who suggested it? Was it?
I actually first said about the medium point and the Schwartz line.
Oh yeah, sorry. That was Stefan's suggestion. Yeah. So yeah. So basically, Stefan was trying to use that exactly what you just said. So yeah. But yeah, I mean, this seems much simpler than the original problem, right? Show that J, U, and S are collinear. So yeah. It almost feels like Desargues' theorem, Chebian's nest. I think I've heard of that before. What is that? Yeah, because this looks so. So let me draw AB. Because this whole configuration looks, because we have like D and then the intersection of B, F. Like we have FHD and EQD, and we draw like the intersections through the respective points.
Draw CH and the BQ alliance.
CH and D and BQ.
BQ. Let them intersect AC and AB.
Okay. Sorry. I'm going to call that W over here.
Now, by Pappus's theorem, if we let VE and WF intersect, then that would lie on SU.
Okay.
So maybe we can show that some combination of those points lies passes through J.
Interesting. Okay.
I think I solve it by Savian's nest.
What is the Chevian's nest theorem?
It basically says so we know AD, BE, and CF are concurrent, and DJ, EH, and FQ are also concurrent. So it basically says then BH, CQ, and AJ are also concurrent.
BH,
I mean, yeah.
BQCH and BQCH and JU. Okay, is that like that's really interesting, that theorem. Is that like a form of Desargues theorem or something?
Yes, it's I guess it can be proved by the Desargues involution theorem.
Ah.
And now we just use it for the triangles BCU and DEF and HQJ.
HQJ. Let me see. Could it? What if I just try to use Desargues theorem on JHQ and BSC? How would that work? So, so if I have JHQ and BSC,
actually, Savian's nest is not so complicated. Yeah.
Okay. Okay. So Chevian's nest theorem. I'll just write out the two. So Chevian's nest on ABC, DEF, and JHQ.
No. BCU, HQJ, and EFD.
BCU, HQJ. BCU, HFJ.
HQJ.
Sorry, HQJ. My memory is not too good. And EFD.
Yes. So it's immediately implies that GUS is collinear, R collinear.
J, U, and S are collinear. Okay. I'll have to read more about it. It sounds like a really interesting theorem.
It's very easy to prove.
Okay.
It is like just a combination of the Chavez theorem and the trigonometric form of Chavez theorem.
Okay. So, yeah, this will be a while to write out the full proof of this. But I always like learning new theorems like that. So yeah, thanks for bringing that up. So do you guys think I should write out the, so let's see. So I'm going to delete points V and W. I'm going to write up this proof as quickly as I can. It would take a long time to write the whole proof. Yeah. You guys want to move on to the next problem? We solved it. It's an amazing proof. Yeah, maybe if we finish the next problem then I'll type up the solution to this one. But this is like a really amazing solution. I like how we combined everyone's ideas. So thanks for that.
I agree. That was a really nice problem.
Yeah. All right. So let ABC be a triangle with circumcircle gamma, circumcenter O, and orthocenter H. Let me draw the orthocenter. I could have probably just typed circle ABC, but. All right, so O is the center of it. Oh, whoops, this should be H. And M and N are the midpoints of AB and AC. Yeah, that was an awesome last solution. I did not think we would, I was not sure we would get through it, but that was really cool. E and F are the phi to the altitudes from B and C. So they're going to pass through H, of course. Let me cheat. Draw E and F and then delete D. P is the intersection of MN with the tangent line. I feel like I've seen a lot of problems like this, where you take the intersection of MN with the tangent line from A. And then there's lots of like radical axis things going on. So P is this point. And Q is the intersection point of, okay, so we draw that same circle from a previous problem and it intersects at Q. So Q is the, I think it's literally called the Q point, right? But it's spelled Q-U-E-U-E. So R is the intersection of AQ and EF. And I don't think it lies on MN. And we want to show that PR is perpendicular to OH. All right.
R lies on BC. That's what we have proved earlier.
Okay. Yeah, we proved it in that other problem. And yeah, that's just the radical axis theorem.
Sorry, Michael.
Mm-hmm.
Can you close the intersection of line MN and EF?
Hold on one sec. So did you say draw the intersection of MN and EF?
Yes. And
Okay.
we have a common result that AD is perpendicular to OH.
AD is perpendicular to OH.
Yes.
Interesting.
We need to prove that AD is parallel to PR.
All right. How do you know that AD is perpendicular to OH?
I can't remember the solution, but I remember that you can use the radical axis.
Okay. So something using the radical axis theorem.
Then what can I see from that? So if we take AD and OH, then it would intersect on EHF, which is, I mean, like equivalent to what he said.
Oh, so you're saying OH would pass through this point right here. Okay. All right.
Can you intersect AD with the circumcircle again?
Yeah. Just a sec.
So we want to show AR bisects PD. I think we can project through A to
Okay. Project through A. So project P, J, and D through A onto the circle.
Yeah.
Okay. So J goes to Q, P goes to A, and D goes to I. And then we want to draw the parallel. All right. So this is point K. And AK is tangent to this circle, I think, right? Yeah. So basically we want to show that QAIK is harmonic.
Look at the chat, Michael.
Okay. If we can prove OH is perpendicular to AD, that solves it. PR. So we don't even need the parallelogram. By the midline, J is the midpoint of AR. Oh, yeah, you're right. Since DE is parallel to the tangent, because yeah, that's well known. So okay, so we already know it's a parallelogram by that. Okay, so we want to show OH is perpendicular to AD. So that's what Nguyen said, but let's see if we can remember the proof. All right, so I'm going to delete K and I for now. I wonder if E, G, and J are collinear. I don't think they are. I'm just curious. No. Okay, so we want to show OH is perpendicular to AD. We know that OH is the Euler line, so we could also use the 9-point circle maybe. Let's see. So this is EFNM, that's the 9-point circle. So we could, if we draw the center of that, it's going to lie on OH, right? So we could call it K.
It will be the midpoint of OH.
Yeah, it'll be the midpoint of OH. Maybe we could show that OK is perpendicular to AD somehow. Wait, isn't that, wait, I mean, angle AGH, sorry.
OH, FN, and ME should concur. That is actually sufficient by Broca's theorem.
Hold on a sec. So sorry, I'm just my brain. So I'm a little confused. So we want to show that OH and G are not collinear. I kept thinking they were. So it's like what? But or OH isn't it like we wanted to show OH is perpendicular to AD, but isn't it true just because like this circle, like angle AGH is 90, or am I, what am I missing here?
I think, yeah. I mean, circle of AM and just finished. OH is perpendicular to AD.
But why can't we just use, how did we define G? Is G just where OH meets the circle? Oh, okay. We just wanted to show that AG, okay, we wanted to show that AG, EF, and MN concur. And okay, in order to show they concur, we had to show that. Okay, I'm just, okay, so we want to show, yeah, ME, NF, and OH.
Michael.
Sorry, Michael. I have just remember the solution to prove that AD perpendicular to OH.
Okay.
It's quite easy.
Michael. Oh, okay. So just stop me. Sorry.
So just use the radical axis. So can you draw the circumcircle of AMN?
Yeah. So and it passed through O, right?
Yes. And we easily have that EFMN are concyclic, right?
Yeah. Yes.
So dF times dE is equal to dm times dn. So the lies on the radical axis of triangle AMN and AEF.
Okay.
And we have the center of circumcircle AMN is the midpoint of AO, and the circumcircle of triangle AF is the midpoint of AH. So AD is perpendicular to the midline of triangle AHO. So AD is perpendicular to HO.
Okay. So like once we know that O, okay, so let me write this from the start. So first, basically, you showed that A, G, EF, and MN are concurrent at point D, right?
No, you don't. Okay, so let's say Michael.
Yeah.
So let's say because the triangle or the circumcircle of AMN is tangent to the circumcircle of ABC, right?
Mm-hmm.
The homothency. So
Yeah.
PA will be the tangent of circle AMN too.
Okay, so AP would be the tangent to both circles, right? That's the radical axis.
Yeah, so PA square will be equal to BM times BN. So P will lie on the radical axis of the circle K and circle O.
Okay. All right.
And RE times RF is equal to RB times RC. So R lie on the radical axis of K and O as well. So PR is perpendicular to KO, which is OH.
Oh, that's really simple. Okay, I think that's the simplest solution. I think we found a whole bunch of different ways to do this, but yeah, I think that is definitely the easiest of them. So yeah, this is the first time in a while where we solved all 6 problems. So I guess maybe they're just a little easier this time. So we don't need a lot of stuff actually for that proof. That's a very simple proof. So the circle AMON has diameter AO. Is tangent to ABC. So we have PA squared is PM times PN. So MFEN all is cyclic since they all lie in the 9-point circle. And so PA squared is PM times PN. So P lies on the radical axis of the circle O and the circle K. I feel like we did this problem once before, maybe. It was a long time ago, though. And then similarly, R lies on the radical axis because RF times RE is RB times RC. So first I'll just say BFEC is cyclic. So RF times RE is RB times RC. So R also lies on the radical axis of those 2 circles. So PR is the radical axis of O and K. This implies PR is perpendicular to OK. Oh, we didn't even define point K, but PR is perpendicular to OK, and so PR is perpendicular to OH. So I'll say, let K be the 9-point center of the circle ABC. So K is the midpoint of OH. So we got through all of them. I don't think we'll have enough time for another.
We could do the previous. I solved it.
Oh, so we solved. I think we solved all of them, right? We could write it up though, right?
We don't need the point U. We will prove Fj and midpoint of KD is collinear. We don't need U.
Okay, we don't need point U. We can prove that Sj and the midpoint of dk are collinear.
Yeah.
Okay. Let me get rid of all those. It came back.
Okay. Okay. Could you draw HQ, JH, and JQ?
HQ, JH, and JQ. Yes. All right.
Okay, so now we gotta prove angle JHS is equal to angle JQS.
Okay.
And that is kind of similar because if you call BQ and cut FD at one point.
BQ and FD. Okay, so that point right there.
Yeah.
There we go.
Yeah, and yeah, as well. So let's say angle JQS is equal to angle HVB, right?
JQS is equal to HVB. Yeah, because they're parallel.
Yeah, and HVB is 90 degree minus HVB, right?
HVB, yeah, because these are perpendicular, so it's 90 minus HVB. Okay.
And yeah, and that will be 90 minus QCW.
Basically, BHQC is cyclic, is what you're saying, right?
Yeah. So angle V is equal to angle W.
Okay.
So angle H will equal to angle Q.
Okay.
Yeah. So could you draw SJ?
SJ, yes.
Yeah. And we will define M as SJ cut HQ.
Okay. So I'm gonna hide DK for now.
No, don't hide. Yeah. Could you rename H as P? That will be better.
Okay.
Yeah. Okay. So MP over MQ will be equal to sine PSM over sine QSM times PS over SQ.
Okay, so I'm a little confused here. So, how do we define M?
And SJ cut PQ.
So do we know it lies on BK?
No, we will prove it on DK, and we will prove it as the midpoint of DK.
Okay, all right. So we'll prove both those things. Okay.
Yeah. Because if we prove it line DK, it must be the midpoint because PQ is the midpoint of DF and DE.
I see how you're doing it. So you want to show that PM over MQ is FK over KE, and then that would solve the problem.
Yeah.
Interesting.
So first we will calculate sine PSJ over sine QSJ. Could you draw or could you write after what I say? Okay, so
PSJ. So
that the did you prove that PM over MQ is equal to BD over DC?
What?
PM over MQ.
DM
Is
over
equal-
MQ?
PM.
BD or equals to BD over DC.
I haven't proved it yet.
That is actually true, and that is sufficient.
Yeah.
Okay, so okay, you could share your solution. Yeah. Because the way I calculate MP over MQ, we just need to prove that equal to KF over KE. Yeah, just to say it. Yeah.
I'll just move this to the side a little, just so I can type this up and we can see it at the same time. So, so we have PM over MQ. That's the sine of what were the signs you're saying?
Yeah, sine
of
PSM over sine QSM times PS over QS.
PS over QS.
Yes. Yeah, and okay. Just enter. We will calculate sine PSM over sine QSM.
Okay.
And so let's say PJ over sine PSJ.
PJ over sine PSJ.
Yeah, is equal to JS over sine JPS. Equal to JS over sine JPS. Yeah. And because angle JPS is equal to angle JQS, so that will be equal to JS over sine JQS. Yeah, and that will be JQ over sine JSQ.
All right.
Implies that sine. Yeah, implies that sine PSJ over sine JSQ
Equals PJ over JQ.
Yeah. Yeah.
Which
So-
is DE over DF. Yeah. Okay.
No, we don't need that.
don't need
So and that will equal to DQ over DP.
DQ over DP.
Yeah, DQ over DP.
Okay.
So now MP over MQ will be equal to DQ over DP times PS over QS.
Okay, so this is DQ over DP.
Yeah, and PS over QS is PP over QC because BQC is cyclic.
DP over QC.
Yeah. Yeah. So and PP over DP, triangle BPD is similar to DKE.
EPD is similar to CQD, right?
No. PPD is similar to DKE.
DKE. Okay.
Yeah.
So
So PP over DP.
BP over DP.
Yeah, it's equal to KE. It's equal to let's say DK over KE.
DK over KE.
Yeah. Times, yeah.
DQ over QC.
Yeah. And DQ over QC is as well as DQ over QC is KEF over KD.
KF over KD.
Yeah. And that will be KF over KE. So KM and D is collinear.
Okay. So this is KF over KE.
Yeah.
So then we have DK and M are collinear.
Yeah.
So
M will be the midpoint of KD, and that will solve the problem.
all right. Let me just write that for a sec. All right, so I think it's about a good time to stop, but that's a really interesting other way to do it. So thanks for bringing that up. Thanks everyone for participating. If you would, so I see someone just asked a question in the chat. It was a little bit of a long proof, so we could discuss it more in Discord. But yeah, thanks everyone. Sorry about the rain today, but this is a really cool session. It's been a while since we've gotten through all 6 problems. So if you'd like to join future sessions, feel free to email me at mgreenb801@gmail.com. They're on Sundays at 8 a.m. US Central Time. Thanks everyone, and have a good day.